Welcome to the Software Engineering channel on YouTube. Today we're going to start with a brief history of programming and computing throughout the 20th and early 21st century. So we will start with the IBM Mark I, which was built in 1944. It used punch cards as input and weighed over 50 tons and was over 50 feet long. Obviously making it very portable for students to take to and from class. In the late 1940s, we had John von Neumann coming up with a design to put components to the computers and group them logically. So you have the arithmetic logic unit, the ALU, the control unit, memory, and input-output devices. These are the same basic components we still use in modern computers, and this design allowed for programming instructions and data to be stored in the same memory space, which is an important innovation. In the 1950s, we saw the introduction of high-level languages like Fortran and COBOL. We also saw that transistors were being replaced by small-size integrated circuits, otherwise known as chips. And in the 1970s, these chips allowed the invention of the microprocessor, which is the entire central processing unit, the CPU, on a single chip. And later in the 1970s, 1977 to be exact, Steve Wozniak and Steve Jobs finished building their first Apple personal computer in their garage. Fast forward a little bit to the 1980s, you have IBM developing their version of a personal computer, and you have a bunch of clones of it called IBM Compatibles that made it more affordable to the common consumer. So computers were being widespread, not just sitting in research facilities and universities. In the 1990s, the internet has become widespread, and computers are starting to gain more power, your memory is getting smaller and more efficient, and your processors getting faster and faster every year. You mentioned the components that von Neumann had designed. Like I said, we're still using largely these same components. The CPU is the brain of the computer. This is the more powerful the CPU, the faster it can perform arithmetic and logical operations. You also have main memory, otherwise known as random access memory or RAM. This is directly connected to the CPU using a memory bus. All the data that is brought into all data must be brought into main memory before it can be manipulated. Each memory cell has its unique location or an address, and today's computers have billions of memory cells. This is temporary storage, so when the power goes off, all the memory that's in there is garbage, lost. So how do we store the data permanently? That's where secondary storage comes in. This is your hard drives or your flash drives, etc. This is permanent storage, and the information must transfer from a hard drive to RAM in order for it to be used by the CPU. Early on, these were typically magnetic drives, and magnetic drives are still fairly common, but a lot of the newer stuff is also solid state. Then you have input-output devices. Your keyboard, your mouse, your monitor, your speakers, your network cards, etc. This is how the computer, you provide input, or how the computer gets input, and how it provides output to either to the user or to the network or some other computer. And moving on to the focus of most of the lectures on this channel, which is the software, which is how the instructions that tell all these components what to do. Each bit of software is written to perform a specific task. You have system programs, like operating systems, that control the computer overall, and then you have application programs that do very specific things, like word processors, spreadsheets, video games, etc. So, in the software, how do we tell a computer what to do? As I mentioned earlier, the IBM Mark I used punch cards. These were plastic cards. You had holes punched in them that meant, told the computer to do a specific instruction. You'd pull a lever, it would run the instruction, you'd pull that card out, put the next one in. Obviously it's very tedious, and you also have to make sure that the cards are in the right order, otherwise you can really screw things up. So moving out of the punch cards, we developed binary, which is ones and zeros in electric currents that would tell the computer the same thing, but it was stored actually in the memory of the computer instead of on physical cards. This allowed the creation of machine languages, where those ones and zeros meant specific things. However, the machine language was very difficult for programmers to work with, so we developed assembly language, which is a human-readable version of the machine language. It's easier for humans to understand what's going on. However, it still requires the programmer to think in terms of individual machine instructions. Enter high-level languages, human-readable languages that allow the programmer to think in terms of programming constructs. These are typically compiled into machine language using a compiler or interpreter, depending on the language. Some examples are Fortran, COBOL, C, C++, C#, Java, etc. For the lectures on this channel, we'll be using C++ as the teaching language. C++ has a wide array of features that allow it to be used for teaching many different constructs and paradigms that can also be used in other languages, but it has a support for all of them, so it makes it a good choice as a teaching language. So up next will be your first C++ program. So stick around for the next video.